Welcome back to our IB Physics video series. This is the third and final video in our IB Physics Topic 8 video series, Energy Production, where we will be looking at Earth's energy balance and the greenhouse effect. Make sure to watch our previous IB Physics Topic 7 video series, as this video builds on the content covered there. In the IB Physics exam, you could be asked to use laws of thermal energy transfer to describe Earth's energy balance. Let's look at this now. Earth's energy balance can be summarized into three principal sections. The Sun produces light that is incident on Earth, the light is partly reflected and partly absorbed, and the absorbed light is re-emitted as heat. Understandably, you need more detail for your exam. The Sun's incident light is termed the solar constant. This is officially defined as the incident solar intensity above Earth's atmosphere, often given a value of 1,360 watts per meter squared. You are expected to calculate this intensity in your exam from provided values for the Sun's radius, 6.96 times 10 to the 8 meters, the average distance from the Sun to Earth, 1.5 times 10 to the 11 meters, and the Sun's surface temperature, 5,780 Kelvin. When doing this calculation, assume that the Sun is a perfect black body. First, use the equation power equals Stefan-Boltzmann constant times area times temperature to the power of 4. So, find the surface area of the Sun, i.e. a sphere, using the equation surface area equals 4 pi r squared, and substitute in the Sun's radius, giving 6.09 times 10 to the 18 meters squared. Then, substitute in values for the Stefan-Boltzmann constant, area, and temperature, and solve for a solar power of 3.85 times 10 to the 26 watts. Since intensity decreases with increasing distance, i.e. from the Sun to Earth, and radiation spreads as a sphere, by the time this power reaches Earth, it's radiating in a sphere of radius 1.5 times 10 to the 11 meters. Thus, to calculate intensity at Earth, use intensity equals power divided by area. Then, find the surface area of this new sphere by substituting the distance to Earth into the same formula, which gives 2.83 times 10 to the 23 meters squared. Finally, substitute in the values of power and area and divide to get an intensity of 1,360 watts per meter squared. Remember this calculation, as it comes up often. Note that this value is above Earth's atmosphere, as much of this intensity does not reach the surface due to four main factors: Earth's surface area, latitude, axial tilt, and atmospheric conditions. Let's cover each one. Earth's surface area causes solar light to spread over a larger area, decreasing its intensity. This is because the incident light that hits Earth can be approximated to be a circle with an area of pi r squared. Even though half the Earth is lit at any time, the Earth rotates, so the incident light is spread across the entire surface every day, with a surface area of 4 pi r squared. Remember that intensity equals power divided by area, so if area increases fourfold, intensity decreases by fourfold. Thus, 1,360 divided by 4 is 340 watts per meter squared, spreading across the entire surface. The effect of latitude means that areas further away from the equator receive a lower solar intensity because the same rays of sunlight must travel further through the atmosphere and are spread over a larger area. Earth's axial tilt changes the impact of latitude and thus causes different seasons. During March and October, there is little tilt. Thus, the equator receives the highest intensity sunlight. During June, the northern hemisphere is tilted towards the Sun, and thus receives the highest intensity sunlight. During December, the southern hemisphere is tilted towards the Sun, and thus receives the highest intensity sunlight. For atmospheric conditions, clouds mainly reflect sunlight. The atmosphere absorbs sunlight, and both scatter sunlight to produce sky radiation, i.e. the blue sky colour we observe. As a result, the Earth's surface, on average, only receives roughly 240 watts per meter squared of sunlight. However, this would warm the Earth to only minus 17 degrees Celsius. So how is the Earth so warm? Well, we can thank the greenhouse effect. The greenhouse effect is the process by which atmospheric gases absorb infrared radiation emitted from Earth's surface and re-emit it. Such gases are termed greenhouse gases, and include methane, water, carbon dioxide, and nitrous oxides. Methane is naturally found in gas and produced by the decomposition of dead plants or livestock flatulence. Water is naturally found as water vapour in the atmosphere. Carbon dioxide is naturally produced by forest fires and volcanic activity, and nitrous oxide is naturally produced by livestock. You must also recall how humans contribute greenhouse gases. Methane levels are increased by farming livestock and crops. Carbon dioxide levels are increased by deforestation and fossil fuel combustion, and nitrous oxide levels are increased by the fabrication of nylon and farming livestock. So how do greenhouse gases cause the greenhouse effect? Well, the process is as follows. You've now reached the end of the preview for this IB Science video. If you want to check out the full video, head over to our website and select a membership plan today.